Welcome back to Fundamentals of DC Circuits. In this video, we're going to discuss two theorems, Thevenin's theorem and Norton's theorem. The learning objectives for this video are basically that you'll be able to apply both Thevenin's theorem and Norton's theorem to simplify a circuit for analysis. Thevenin's theorem is a theorem that we can use to simplify a very complex circuit into something much simpler. The theorem consists of a few steps that help you to create what we call the Thevenin equivalent form of a resistive circuit. The Thevenin equivalent circuit consists of a voltage source, which we call VTH or V Thevenin, and a resistance, which we call RTH or R Thevenin. The circuit that you will create by using Thevenin's theorem gives you a circuit that is 100% equivalent to something that's far more complex. So it's a simplification tool. Here's how we define the two elements of a Thevenin equivalent circuit. First, you have the Thevenin equivalent voltage. That voltage is equal to the open circuit, or what we call the no-load voltage, between two output terminals in a circuit. The Thevenin equivalent resistance is the total resistance appearing between the two output terminals in a given circuit with all sources, voltage sources and or current sources, replaced by their internal resistances. Remember, to replace a voltage source with its internal resistance, you're going to just replace it with a short circuit. So a Thevenin equivalent circuit is not the same as the original circuit, but it acts the same in terms of output voltage and output current. For example, let's say that this is the circuit you want to create a Thevenin equivalent for. Points A and B are where a particular load may be connected. We're not so much concerned with the load, but we're concerned with creating a circuit that's simpler than this that we can connect the load to. The Thevenin voltage is the no-load output voltage between points A and B, meaning there's no load here. We don't have a load resistor at all. We're simply going to figure out what the voltage would be between these two terminals without a load. That's what the no-load or open circuit voltage means in the definition of Thevenin voltage. So if this were your circuit and you had no load connected here, just a voltmeter, you'd have current that flows this way. And then you would think that current would split here, but not if this is an open circuit with nothing connected to it. Again, this is just a voltmeter. That's not a resistor, so this represents an open circuit. There's nothing connected here. So really, when you consider the Thevenin equivalent voltage, you're really finding the voltage across R2. Because there's no voltage here, because there's no current here, this might as well not exist for this piece of the problem. So when I find the voltage from point A to B, I'm really just finding the voltage across R2 because all of the current is going to flow through R2. That's how you find your Thevenin voltage. With your Thevenin resistance, you replace your source with a short. And then you kind of imagine, if I had a voltage source here, what resistance would that voltage source be connected to? If the voltage source were here, R1 and R2 are in parallel. R3 is in series with that parallel combination, and that's your Thevenin resistance. Once you have found your Thevenin voltage and Thevenin resistance, you simply draw a diagram with your equivalent circuit. So now, instead of connecting your load from these 2 points, you can connect your load to these 2 points, and you have a much simpler circuit to connect your load to. That's the whole idea behind a Thevenin equivalent circuit. So we'll do some examples to apply the theorem. Here's our circuit. Here's the load. We're going to find the Thevenin equivalent circuit between points A and B. And we're going to apply those steps that I showed on the previous slide to do that. To begin, we're going to find the Thevenin, the Thevenin voltage. To find the Thevenin voltage, the first thing you're going to do is remove the load completely. Just completely remove it from your circuit. And determine the voltage between the load terminals, between A and B. In this case, with no load connected here, this is an open circuit, so there's no current flowing anywhere here. If I want to find the voltage from this point to this point, I'm really finding the voltage from R2 and R3. Keep in mind that current will flow this way and down and around. So I need to find the voltage across R2 and R3. That's going to be my Thevenin equivalent voltage. I can find the voltage for R2 and R3 using a voltage divider. On the top of my voltage divider will be the resistance that I want the voltage for, which is R2 and R3. So I'm going to add those up and put that at the top. The bottom will be the total resistance in the circuit, and then I'm going to multiply by the source. So V Thevenin comes out to be 4.08 volts. That's how we find our Thevenin voltage. Remember, all you're doing again is removing the load completely and finding the voltage from point A to B. Remembering that this piece here is an open circuit and there's no current flowing here. Our next step is to find the Thevenin equivalent resistance. To do this, we have to remove the load, which we did in the first step as well. Completely take off the load. Replace the voltage source with its internal resistance, which would mean we short it out. And then determine the amount of resistance seen between the load terminals A and B. So again, just imagine if a voltage source were here, and if current began to flow through the circuit, what would the resistance be? So if you look at R1, R1 is in parallel with this branch. So R1 is in parallel with the combination of R2 and R3. Once I combine these three resistors together, that combination is in series with R4. So when I add all of that up, I'll have my Thevenin equivalent resistance. So our Thevenin is going to come out to be R4 plus R1 in parallel with R2 and R3 combined. I'm going to add R2 and R3 together, then find the parallel combination of R2 and R3 together with R1, then add R4 to it. That's your Thevenin total resistance. Once you're done, you have to draw the equivalent circuit. And this is your equivalent circuit showing V Thevenin and R Thevenin. And your load would then be reconnected right here between A and B. When you draw the equivalent circuit, make sure that you label this as R Thevenin and V Thevenin, so it's very clear that that's a Thevenin equivalent circuit. Keep in mind, this circuit and this circuit are equivalent. They deliver the same voltage and the same current to the load, but the one on the right is far simpler to build and to analyze than the one on the left. So we use a Thevenin equivalent circuit when we want to simplify a complex circuit into something simpler to use. In the next example, we're going to determine the Thevenin equivalent from different terminals. If you look at this circuit, it's really just a series circuit. R1 is in series with R2, which is in series with R3. We just have different points of view we're going to consider. These are just points of view. So for the first part, we're going to figure out the Thevenin equivalent if our point of view is from point A to point C. Then we're going to do it again if our point of view is from point B to point C. So these are our points of view. Point A to point B to point C, or from A to C. So here are the 2 points of view we're going to consider and do a Thevenin equivalent circuit for. Let's start with figuring out the Thevenin equivalent if our point of view is from point A to point C. So imagine my load is eventually going to be connected right here. That's where my load will be. We're going to begin by finding V Thevenin. We're going to remove the load, which in this case, the load was never given. But if the load were given, you would completely remove it. And we're going to determine the voltage between points A and C. The voltage from point A to C would have to be the voltage across R2 and R3. So we're simply going to do a voltage divider once again to find that Thevenin voltage. There's my voltage divider from point A to point C. showing on the top the combination of R2 and R3, and on the bottom is the total resistance multiplied by the source. Next, we have to find the Thevenin resistance from points A to C. So look very carefully at the picture, and again, this is how I like to imagine it. If the voltage source were right here, what kind of resistance would we see? Remember, we have shorted out the original source. So that means that R1 is now in parallel with R2 and R3 combined. That's how we get our R Thevenin. So again, remove the load, short the source, and determine the amount of resistance seen between load terminals A and C. That would have to be R1 in parallel with the combination of R2 and R3. Lastly, you're going to draw the equivalent circuit. There's my Thevenin equivalent showing the point of view of point A to point C. Next, we're going to determine the Thevenin equivalent for this circuit from terminals B and C. So our point of view is now changed. The load is now going to be connected from point B to C. Now let's look at what would change with our calculations in this problem. First, we're going to find the Thevenin voltage. To do that, remove the load, which in this case, again, it was not given, so don't worry about that. But it will be given in future problems, so you will remove the load. Determine the voltage between points B and C. Now I want the Thevenin voltage just for R3. So I'm going to do a voltage divider, but this time my numerator is just going to have R3 instead of R2 and R3 like before. So my Thevenin voltage comes out to be 2.43 volts when I perform that voltage divider. Our next step is to find our Thevenin. To do that, you have to remove the load, which we've already done, short the source, and determine the amount of resistance between points B and C. Look very closely at this picture. Imagine that your voltage source is here now. What type of resistance would be seen? We can see that R1 and R2 are in series, and those two combined are in parallel with R3. Because if there were a source here, current would go here and it would split. Here's one path, here's your other path. So I'm going to compute R Thevenin by doing the parallel combination of R3 and the sum of R1 and R2. And lastly, you're going to draw the equivalent circuit. There's my Thevenin equivalent if my point of view is changed to be from points B to C. In the next problem, we have a bridge circuit. This diamond orientation here is called a bridge circuit. We're going to determine the voltage and the current for the load resistor RL in the bridge circuit below. This is a little bit more complex, but this is a great exercise in understanding how we can create a Thevenin equivalent circuit that will be a lot simpler than this one. To begin, remove RL, remove the load. There's your 2 points, your 2 points of view for where you have to find V Thevenin and R Thevenin. Now we're going to redraw this circuit because the diamond configuration can make it a little hard to see what's in series, what's in parallel, things of that nature. So you can stretch out that diamond to form a rectangle. And if you do that, it'll look like image B. Now we have to find V Thevenin, which is the voltage from point A to point B. Since point A and neither point A or point B are connected to ground, the voltage from point A to point B is simply the difference between the two voltages at those 2 points. So we have to find the voltage at point A, find the voltage at point B, and subtract them. The voltage at point A is technically this entire line here. The voltage at point A would be the voltage from R2 to ground. Point A is technically this node. The line here is connected to the node, so point A is connected to this node. The voltage at point A would be the voltage across R2. I can use a voltage divider to find the voltage across R2 because R1 and R2 are in series, and as a combination, I know that the voltage across these two combined is equal to the source. That voltage is going to divide among R1 and R2. Therefore, I can use a voltage divider to figure out how much voltage is across R2. That's what you'll see right here. The voltage at point B is simply the voltage from point B to ground. The voltage from point B to ground is the voltage across R4. And again, I can use a voltage divider to figure out the voltage across R4. I know that R3 and R4 combined have to have a total voltage of the source because these are in parallel with the source. These are in parallel with this group and the source. We have two parallel branches here. So I can use a voltage divider to find the voltage for this piece of the second parallel branch. That's the end of finding my Thevenin. Now you're going to find Thevenin. Remember that you have to replace Vs with a short. That's right here. And we have to figure out Thevenin. Here's where this gets a little tricky. So the book has a nice tool that can help. We can redraw what we see in image D with this configuration right here. Notice that the red lines on this diagram represent the same electrical points as the red lines on part E. Sometimes we have to redraw and get a different perspective to figure out how to combine elements together. Once we use this tool or this diagram to redraw what our circuit would look like when we need to find the equivalent resistance, we can see that R1 and R2 are in parallel, R3 and R4 are parallel, and those two combinations are in series. Another way to look at that might be to imagine a voltage source right here. If current flows this way, it has two paths. This is one path, this is one path, and those two paths recombine right here. So R1 and R2 have to be in parallel. Then we have the total current that flows this way into that node. And we have current here that flows this way into that node. We have, again, two paths. So the total current is here. It splits. R3 and R4 are two parallel paths where current splits and comes back together right here. So they're also in parallel. This diagram is a much easier way of thinking about that. Once we have Thevenin, we're done and we can draw the equivalent circuit. And this is how we would analyze a bridge circuit, no matter what R1, R2, R3, and R4 would be. So now that we've gone over the basic principle behind this, we can use that information from the previous slide and simply plug in the numbers with the problem that's given. So we're going to find Thevenin by removing the load and determining the voltage from load terminals A to B. Remember, these are the steps we just discussed to do that. So I can say that Thevenin is going to be the voltage at point A minus the voltage at point B. The voltage at point A will be a voltage divider between these two resistors. The voltage at point B will be a voltage divider between these two resistors. And I'm following this formula right here and simply plugging in what I know for R1, R2, R3, and R4. So you get a Thevenin of 5.32 volts. To find Thevenin, we're going to use this information here and plug in our values for R2, R3, R4, and R1. So Thevenin comes out to be R1 in parallel with R2 plus R3 in parallel with R4. Then you're going to draw your equivalent circuit. That's your Thevenin equivalent for the bridge circuit shown on the left. Notice this is far simpler than the bridge circuit shown. That's it for Thevenin's theorem. Now we're going to move on to Norton's theorem. It's quite similar to Thevenin's theorem. Thevenin's theorem is used when you have a voltage source. Norton's theorem is used when you have a current source, or you want a circuit with an equivalent current source, I should say. A Norton's equivalent circuit will have a current source right here with our Norton equivalent current, and it'll have a parallel resistance with a Norton equivalent resistance value. I sub n, the Norton equivalent current, is the short circuit current between two output terminals in a circuit. Short circuit current. That means we're basically going to put a short between our two terminals and figure out the current going through that short. Norton's equivalent resistance is the total resistance appearing between the two output terminals. So when you calculate Norton's equivalent resistance, you're basically calculating it the same way you would have calculated your Thevenin equivalent resistance. So to determine the Norton equivalent for this circuit, we're going to start by removing the load. Remove the load and then remove it and replace it with a short. So not only did we take the load away, we replaced it with a short. So to find the Norton equivalent circuit, you have to figure out the current going through the short. That's your Norton equivalent current. In this picture, if this is a short, current's flowing this way. R3 and R2 have to be in parallel. Combine those together, and that has to be in series with R1. So there's your total resistance. Then you can find the total current in the circuit by doing Ohm's law. So I know the total current that flows up here through R1 and then splits right there at that node. I just need to figure out how much went through R3 because that will tell me how much went through the short and give me my Norton equivalent current. So let's perform a current divider to do that. Remember, your current divider has to have a numerator that is the parallel combination of your two branches. The denominator is going to be the value for R3, and you're going to multiply by the total current going into this node before it splits. So you get a Norton current of 20.24 milliamps. Next, you're going to find your Norton equivalent resistance. To do that, remove the load. Also remove the short from point A to B. Make this open. Short your voltage source. And determine the amount of resistance from terminals A and B. So that's a lot of steps. Make sure you've got the steps. Remove the load. Remove the short between points A and B. So make this open. Short the voltage source. And then figure out the resistance from point A to point B. In this case, R1 and R2 are in parallel, and then R3 is in series with that parallel combination. And now you have your Norton equivalent resistance. Step 3 is to draw the equivalent circuit, which would look like this. In this case, we have a Norton equivalent current, so we have a current source, and we have our Rn in parallel with that current source. And then the load that you see here, RL, would simply be connected from point A to B. These two circuits are equivalent. They're 100% equivalent. They have to produce the same current and voltage through the load. And that is the end of this video. Please make sure that you get online and check out the practice problems for this concept. It will only make sense with practice. You have to practice all the steps and make sure that you can apply them correctly. So check out these suggested problems online and the solutions that are posted.